Hello, hello. Hello, can you guys hear me? So yeah, we just reached about 100 people already, so I think we can start. So hi, my name is Philip, and we have another instructor, he's Jinhan, and we'll be going through EE0005 revision today. So just a disclaimer, we are not endorsed by the school at all, so we are don't expect any quiz questions or any leaky anything. So we are just here to help you understand maybe the content of the AI more. That's our agenda for this workshop. So before we start, I'll introduce to you what MLDA at EEE does. So MLDA is a student-centric lab which aims to provide a platform to empower all EEE and IM students to learn and deploy ML and data analytics skills and knowledge in both academia and industry. We also do so through our various events, projects, and activities. And as the student committee of MLDA, our mission is to execute and plan those events through our workshops, and we do it through the facilities that we have. So our state-of-the-art faculty, our resource, our technical support to facilitate your journey in machine learning and data artificial intelligence, which is the hot topic of the decade. So we also impact knowledge and skills for machine learning through our 4 different pillars of events ranging from our machine learning projects, industry projects, and career events ranging from workshops and competitions. Yeah, so that's what we do at MLDA. So to start off with, what we need to discuss when we talk about artificial intelligence, we need to define this term artificial intelligence. So simply put, it's just intelligence demonstrated by machines. So demonstrated by machines is quite an easy explanation, but the problem comes actually when we are come to define what is intelligence. So later we will have maybe a few things that we can discuss. But to get you excited about what is artificial intelligence, maybe I can show you a current things that they do that is quite cool, I think. So this is a video, I'm going to play it. So this guy just types in the layout that he wants. And what happens is he presses the generate button and he's able to generate almost a replica of the Google search bar, just based on description. So this is OpenAI's project that was published in May 2020, and it's called GPT-3, which stands for Generative Pre-trained Transformer. So this transformer basically uses natural language processing, and we fed it the web data, and from that it's able to learn, and after that we are able to apply it and generate this kind of results, which I think is very amazing considering machines actually don't understand our language fully. Yeah, so that's one of the demonstrations of AI these days. So in terms of AI, we have these fields, and just now that one is I will consider it under deep learning and natural language processing. But there are actually many other subfields of AI that you can go into if you are interested. So coming back to the intelligence question, so there are many views on AI. So whether an AI can act humanly, this one, whether it can think humanly, whether it can act rationally, or whether it can think rationally. And I would say in terms of acting rationally, AI is in a way there because rational actions can be defined by a set of rules which are very easy to follow by AI. And there are in a way clear-cut rules. Whereas when you're talking about thinking and the human aspect of it, it might be a bit hard to replicate exactly our human nature. So in fact, we have a test for acting humanly, and we call it the Turing test. So Turing test has 3 entities: computer A, machine, B is another human, and C is another human. So what this Turing test is basically this C will talk to A and B, right? They will have a conversation or maybe interrogation, but it's a question and answer. So what A and B have to do is they have to answer and keep basically have a conversation with person entity C, which is a judge. And from after about 5 minutes of this conversation, if C is able to tell that A seems a bit funny and is a machine, then this machine will have said to fail the Turing test. But if A and B are indistinguishable, then A is said to have passed the Turing test. So that is one of the tests as introduced by Alan Turing in the 20th century. Yeah. So then coming that, we have to talk about intelligent agents. So throughout this intelligent agent section, I'll be using this as an example. So this star is actually a agent, which means like an entity, like a robot. You can imagine it as a robot. So he wants to reach this finish line at the end. So this green line I've drawn is so-called the best way that you can go, because it's just straight directly and you reach there. But there are also possible many other ways. So if you go the red route, you still reach your destination, but you might not take the shortest path. So it might take a longer time. So it might not be the optimal solution that we use. Or it might not even end up at the main final destination. It might be going off path and hitting the wall instead. So basically, this is what a definition of a rational agent is. It's an entity that perceives through senses and acts through effectors. So you can say, actually, for us, also we are rational agent, not rational agent, because we can perceive the our environment through our eyes, our sight, our hearing, and we can also affect our environment through our hands, etc. So this is a diagram that depicts what the agent can perceive the environment and the actions. So what constitutes a rational action is basically we will measure some performance measure. So in the case of this one, maybe the performance measure will be what's the distance traversed. So since this is the shortest, so maybe we can try to minimize that performance, and also clear preferences. So again, we refer back to this. You wouldn't want a machine to just keep knocking the wall. So maybe you can have an ultrasonic sensor that always says you must be maybe about 10 cm away from the wall, so you won't keep hitting the wall. So that's hard-coded preferences. And in the end, if you choose the optimum outcome, that is considered a rational action. Okay, so going back to agents, there are many types of agents which increasing complexity as we go down this pyramid. So the most basic one is simple reflex agents. So I would consider, I think if you have done programming before, that will be a reflex agent also, because a program is just a simple program is just you look at some conditions that you have, and then you, in different scenarios, you act accordingly. So that's just simple reflex agents. So going down one step further, we have state. So this one basically means that the agent has memory, which means that it will act based on previous state, the rules again, and the current data that it's seeing. And this tool so far has no goal. So if we want to talk about reaching the finish line, we also need to have a goal in the end. So increasing complexity. So we will ask ourselves, does this action lead the agent to a step closer to the goal? So in the case, we go back to this example, if it goes forward, the distance to the goal decreases. So I would say this is a good action. But if I go backwards, the distance increases. So that wouldn't be a correct action in that sense. And also you have utility-based agents. So again, just now the green and blue, red both lead to the same finish line, but which is the better one? We need this to help us tell which is the best way. So we can have, at every point, we can have certain utilities. Maybe we draw a radius around the goal, something like that, to tell that, oh, this is getting closer to the goal like that. And finally, if you combine all these together, you can even make an autonomous agent which can adapt to the environment through experience. And later we will cover in the last part about reinforcement learning and how this might be achieved. So if we talk about agents themselves just now, we have the agent over here, correct? So then we also need to talk about the environment, the types of environments. So then we have this. So for this example, I will use Minesweeper throughout this whole example. So the first example, first environment type we need to look at is considering whether the environment is accessible or inaccessible, meaning whether the agent is able to get perfect information from the environment or imperfect information. So why sometimes it may be imperfect? Because it might be a hidden example for Minesweeper, it is inaccessible because the mines are hidden. You don't know where is the exact position of the mines. So in that case, it's imperfect. But if you're talking about the case of chess, it is a accessible environment because if you just display a camera up there, there's no hidden pieces. All the pieces of the chess in that particular game is displayed in that moment. And second, we have to talk about whether the environment is deterministic or non-deterministic. So can the next state be completely determined by the current state and action taken? So again, for our Minesweeper example, it is non-deterministic because the mines are randomly placed in different positions. So basically, when I start the game, am I able to know where the mines is? I do not know. So that's why it's non-deterministic. But I got another example here. So another example of the deterministic example is chess, because the outcome of each movement can be determined. So if you have a horse piece, you always move in the L shape. That's what deterministic mean? Because does it have a prefix pattern? Because if you're talking about the Minesweeper, if you click this box, you don't know whether there's a mine underneath, so it might explode or might not explode. It has a chance. So when there's uncertainty involved, it is non-deterministic. Okay, so third one, we have to look whether the environmental is episodic or sequential. So does the agent require the memory of past actions to determine the next best actions, or only current precepts are important? Current precepts means current sensor information. So for Minesweeper, it is sequential because let's say if I open up a place that doesn't have any mine, it will give me some numbers. So then this environment has changed already based on my past actions. That's why it's sequential. And most of environments are actually sequential. Stuff that are not environments that are not sequential, like episodic, they are normally random assigned. So one example will be what is that thing called? Slot machine. Yeah, a slot machine. Regardless of how you play it this time, the next round will be different. And maybe even detecting anomalies in the MRI. This one, the previous image that you detect will not affect the next image that you detect. So that's why in those cases, they are episodic. But if you're talking about a game environment, most of the time it's actually sequential. And also, you have to look whether the environment is static or dynamic. So does the environment change while the agent deliberates? So this word deliberate is, I think, kind of a big word, but it basically means because agents are normally computers, or even us, we have some amount of processing time where we need to think of what the next step to do is. So if the environment changes, example in a self-driving car scenario, while the car is thinking, it would have still been traveling. So it would have changed its position and moved forward already. So in that case, the environment is said to be dynamic. But for Minesweeper, you take 1 year to think about your action, so nothing will happen. So it's static. And finally, we have to see whether the environment is discrete or continuous. So for Minesweeper, we have, let's say, 8x8 grid. So there are 8x8 grids, so there are only total 64 actions that I can make. I can click one of these 64. So they are discrete. So coming back to our self-driving car example, the X direction can be 6.5, or it can be 6.55, or it can be 6.55555 long. It's continuous value. So those domains are not discrete, so they are called continuous also. Okay, so I've covered up this environment. So yeah, here we have a pathway. So I will open a Zoom poll. You guys can actually respond to this. Mm-hmm. Okay, I think I will end it in 10 seconds. Yeah. Okay, so I think you guys can see the results now. So yeah, most of you got it correct. It's actually both partial and fully observable. So this is again relating back to our whether the environment is accessible or inaccessible. So it can have both scenarios. That's why the answer is both partial and fully. Okay. Do you guys have any questions for this one? Okay, I think I'll move on. No one. Okay, so then, so we talk about the types of agents and the environment. So we now have to design how this agent actually solves the problem that we want. So earlier on I said we need to know the cost, whether the shortest path, maybe we try to minimize that. So we first need to do some steps. So we first need to form our goal. So in just now's case, maybe fuel is expensive. So we want to minimize the distance. So example, we can minimize the distance and that will be our goal. Now problem formulation is basically stating our situation out. So this one I'll cover in the next slide. Search process. So this one, we will talk about it later also, but this is basically the flow of what we are doing. And after we finish the search process, we will have found a solution and we have to execute the solution. So that's when number 4 happens. Okay, so goal formulation, let's say we are minimizing distance. So now we need to form our problem. So our initial state is our starting position. So we need to write down initial state is here, this place. Our action set. So what are the allowed actions that we can do? So for this particular case, you can move up, down, left, right in 2D, let's say. Okay. And in the state space, which states are reachable? So this one might be infinite in the case of a very large number in like real life self-driving car scenario. But let's say I put this box as my so-called environment, virtual environment. In that sense, this box will be a finite state because it will not, the entity, the agent over here, it will not go out of the box. So so that means this box is basically this whole box is my state space or where the agent can be. And goal test, what is the goal? And this one may have may have more than one state. So goal test is basically all the paths. So this green one, this red one, it might be another red one over here. All the paths that leads to the goal. That's called a goal test. And so since you have multiple states that will lead to the goal test, so we have a cost function to find out, to help us determine which is the optimal solution. So in terms of cost function, we actually have 2 parts. We have the search cost, which is the offline portion. That means this is the deliberating portion now. And also we have the execution cost, which is the online portion. So we must make sure that we don't waste too much time in the search cost also. So in the event of a self-driving car, imagine for every action the car needs to make, right? It takes maybe 5 seconds for the car to think about what to do. So that wouldn't make sense, right? By the time the 5 seconds is over, an accident might have occurred already. So it's normally important to keep this search cost as short as possible. But so most of the time, right, we will require some trade-off because we cannot find the optimal solution, the global minimum or the global maximum. So instead, we settle for maybe a local solution that will be good enough for our purpose. But this local solution will still lead us in the correct direction. So, like I said over here, the solution can actually be a path or a sequence of actions. So in this case, it's a path actually. So this one you can try yourselves later. I think I'll be sending the slides to you guys after the event. So maybe you can try this yourselves. What are the initial state, the action set, the state space, goal test, and cost function. So now we'll move on, and I think I'll pass it to Jinhan now to talk about search.
Okay, hi guys, can y'all hear me? Okay. So for search algorithms, which are what we need to find the solution. So we are going to traverse the state space along a frontier, which is this red thingy defined here. And this frontier is the foremost unexpanded nodes. And to avoid repetition, we are also requiring a explore set so that we don't explore the nodes that we have already expanded, which is black. And we have multiple strategies for reaching the solution, and I'll cover them next. But before we move into that, we also need to define several dimensions on how our algorithms can be classified. So the first class is termination. So termination is stating that your algorithm is guaranteed to terminate no matter how large is your state space. And second is completeness. Your algorithm is complete if it is guaranteed to find a solution if one exists. And the third and fourth are usually the most important parameters that we care, which is time and space complexity. So time complexity is kind of proportional to the number of nodes that we expand or we generate. And space complexity is related to the memory, which is the maximum number of nodes stored in memory, which can be your stack or queue at any one time. And finally is the optimality, which means that your algorithm is guaranteed to find the best solution if there's one. Okay, so now we can think about the relationship between complete and optimal algorithms. So optimal algorithms are guaranteed to find the best solution, meaning that they can also find a solution. And this definition is the very definition for complete algorithms. So we can say, if your algorithm is optimal, then it is naturally complete as well. Or you can also say optimal algorithms is a subset of complete algorithms. Okay, so now we are ready to move on to the two main types of strategies. So the first one is the uninformed strategies, or we call them the blind search. Because they are really blind, they only use the problem definition, and they kind of don't have no information about the goal state at all. And we'll see what this means later on. And so for blind search, we have two main families of algorithms. One is breadth first search, which expands level by level, and depth first search, which focus on going down. So for breadth first search, we have another variant called the uniform cost search, and depth first search we also has two variants, and we also cover them later. And the next type is the informed search strategies, and this uses information about goal state or we call it the forward-looking knowledge. And here we cover two types of best first search, which is greedy search and also A-star search. So for breadth first search, it is implemented with a first in, first out queue. And for uniform cost search, it is used when the edge weights, which are the value here, are different. So it is implemented with a priority queue. So let us trace the execution of the breadth first search, just to recap a bit. So we start with the node 1. We will call the breadth first search on node 1. So you visit node 1 and you queue it into the queue. And while this queue is not empty, you take the front element and you look for its unvisited children, which in this case is 2 and 3. Both of them has not been visited. So you visit 2 and 3 and you enqueue them into the queue. And so 1 has no more unvisited children, so you dequeue it. And then for 2, you also take the unvisited children, which in this case is 4 and 5. So you enqueue them. And so similarly, 2, 3, 4, and 5 all have no more unvisited children, so you dequeue all of them subsequent. So in this case, the order of visiting is 1, 2, 3, 4, 5. And I'll briefly cover the time complexity and explain what this means. So for time complexity, the worst case is your solution is actually the last one to be expanded. So you have to expand every single node. And the first level, which is only the root, so that's this one here. And the first layer will expand into another B1, B subscript 1 nodes. So this makes B1. And every node in the second layer, you will assume that they will branch into another B2 nodes. So this makes B1 times B2. So if your solution path length is B, and you're going down all the way until the last node, which is the last layer. So you add all the way until this B sub B. And if you denote the maximum branching factor by B, then this expression here is less than this thing. So by the big O notation, you can say this is the big O of B to the power of B. And then the space complexity, remember that we just now talked about this Q. So the space complexity is the maximum number of nodes at the queue at any one time. So for our worst case, which is the node being at the last level, so we have to store every node on the last level after we have queued all the nodes in the previous layer. So we have the number of nodes at the last layer, which is this, and it is also be O of B to the power of D. Okay, so now we'll compare it with depth first search. So it is implemented with a last in, first out stack. And then there are two variants, which is the depth limited search. And this depth limited search is important if your depth state space is infinite, meaning that instead of stopping here, you will go on indefinitely deep. So you have to have a limit, or else your algorithm will just go on and on and on and on. And this iterative deep learning search is actually combining the idea of BFS and DFS. So it actually starts with the depth limited search of limit 1, and then it will go with the depth limit of level 2. So it is actually a for loop, and it goes level by level, which is similar to BFS. And again, we'll give a recap on how this algorithm works. So okay, again, we start with node 1. So we visit node 1 and push them onto the stack. And then for each of its unvisited children, we push them into the stack one by one. So we start with 2, and then we'll push 2 into the stack. And we'll see whether node 2 has any unvisited children, and it does, so it's 4 and 5. But we'll start with 4. So we push 4 onto the stack, and 4. So we have already visited 1, 2, 4. And then 4 has no more unvisited children, so we pop it out of the stack, and the top element is now 2. So 2 actually has still one unvisited children, which is 5. So we push it into the queue. Okay. And 5 is actually a leaf, so it has no children, so we dequeue it. We pop it. And 2 of its children has already been visited, so we pop 2. And we look at this node 1. So node 3 is the only child of node 1 that has not been visited. So we push it onto the stack, and node 3 is also a leaf, so it has no children, so we pop it, and then we pop 1. So the order of visiting is 1, 2, 4, 5, and then we go back and 3. Okay, and then also similarly a brief overview of the complexity. So the worst case for time is still the same, where you have to expand every node. So I'll not cover this again, and so this is similar to the case for breadth of search. But one thing that is different is the space complexity. So it is actually linear compared to the exponential space complexity of breadth of search. So why is this so? So for each node, remember that you need to store the siblings, which is the nodes at the same level. So we say node 3 is a sibling of node 2 to use when you backtrack. So if you reach this node 4, the node 4 down there, and then when you need to backtrack, you need to go back to 2. And then to explore the nodes of the same level, we need to have this sibling, which is node 3. So that is why we need to store the siblings of the same level to use when backtracking. So you, assuming you are going down this path, then the number of nodes that you are storing is this one. And how many nodes that this node 1 branch into, that is B1. And this node, how many nodes does this branch into, and that is B2. We do not take B1, B2, unlike the breadth first search, because we are expanding all the nodes in this level. But in breadth first search, we are only keeping the nodes along this path in the memory. So this simplifies to this B, which is the maximum branching factor B. And so this is B times D, which is linear. Okay, so we have a quiz here. And again, I will open up for all of you to vote. Okay, so consider an infinite depth search tree with a small branching factor, which means that so the branching factor is actually small. Means that it branches only into 1, 2, or 3 nodes at most. Not at most. Like it won't branch into hundreds or thousands of nodes at a given layer. So please try. Okay. Okay, so I guess I will end it now. 5 seconds. 5, 4, 3, 2, 1. Okay, so the answer is of the above. So for infinite depth tree, as I have mentioned just now, if you're just using a simple depth first search, it will go on and on because it will focus on reaching the leaves. So it will go on and on until you reach the end, but there's no end. So it actually goes on and trapped in a loop, so it actually cannot find the solution. And for breadth first search, if okay, let me draw something. Please pardon my drawing. Okay, so assuming you have a lot of nodes here, and this one, you have already ruled out the possibility of it, and it's not correct. So for BFS, you can actually just discard all of this anymore. So you don't need to go through this anymore, so you just look through this. But if you are doing a depth first search, you just go and on and on and on, okay? And yeah, DFS focus on reaching the this is true, I've mentioned it earlier. So located at shallow level, for example here, this is the goal state. And then if you're starting here, for example, and you have lots of nodes here, and so you are focusing on going deep, and then you go here again, and then you go here again, and then you go here again. So, but your solution is here, but you're just going down. If you are using breadth first search, you just search along this level, and that's it. Don't need to do anything anymore. Okay. So I hope this is clear. Any questions? Okay. We'll move on then to informed search. So we need to define an evaluation function, which is what makes the informed search different from the uninformed search. So the first one, which is the one that we use in, okay, actually we use this in the uniform cost search when the age rates are different, which is defined as also the path cost function. So this is backward looking in the sense that it defines the cost from the initial state until your current state. And what makes the informed search different is what beyond the current state. So your heuristic function Hn is forward looking in the sense that it estimates the path cost from your current state to the goal state. So it is only an estimation, and well, it can run off sometimes. But here we define a heuristic to be admissible when it does not overestimate the real cost of reaching the goal. And we are going to discuss two types of best first search here. The first one is greedy search. So greedy, as the name implies, it finds the solution in an incremental manner based on local optimality. So at any time step, it only chooses the best option available at in front of it. Like it doesn't care what the consequence of choosing this node. Okay, so it may not be complete. So, okay, for example, in this case, if you are trying to go from this name to ISERC, so for name, you only have one, you only have one option, which is this path here. And if you reach this ERC, you have two options, which is 87 and 92. So you are going to choose the minimum cost again, which is 87. So you are just going to oscillate here, and you are going nowhere. Okay, for example, you are trying to go here to Fagaras. So if you choose the shortest path or the cheapest path, which is 87, and you reach this point, and again, if you choose the cheapest path again, you are going to just oscillate around. Okay, so here we use a heuristic function, which is an estimate of the distance from your current state to the goal state. So by definition, at the goal, your heuristic function will have 0 value because the distance is 0, right? And another type of algorithm is the A-star search. So this combines the uniform cost search, which use the path cost function Gn, with the greedy search we discussed earlier. So it's the heuristic function Hn. So if you add Gn with Hn, it's the total cost from your start to goal, and you are passing through this node n here. So your evaluation function is the sum of these two. And one disadvantage is it requires an exponential space complexity, as it will store every expanded node in memory. So we have an example here. So we start from this node, the green one, and we shall try to reach this blue one. So, okay, so this thing here is the path cost function Gn, and this little thing in gray here is the heuristic function Hn. So at node A, this green node, you have two options, which is node A or node D. So you look at the Gn plus Hn. So for the evaluation function f of A is G of A, which is this 1.5 plus this 4. So this is 5.5, 5.5. Very ugly, sorry. And for this node D, so your Gn is 2. Sorry. Your Gn is 2 and your Hn is 4.5. So this makes 6.5. So we choose the smallest, the cheapest one. So Fa is smaller, so we go on node A. So similarly, we have two options, which is going this or we go here. So the evaluation function of node B is smaller, 5.5 versus 6.5. So we go to node B instead. So at node B, we still have the option to go to node D or we go to node C. Okay, but in this case, the cost of going to this node D is actually cheaper than the cost going to node C. So we'll backtrack again and we will visit node D instead. So then, yeah, you carry on until you reach this node, this blue node. Okay. Yes, and that's all for search algorithms. Do you have any questions? Please type in the chat or wherever. I'll just unmute. No. No. No.
Hi, may I have one question?
Yes, please.
So I would like to ask about the whether the A star is complete and optional and is time and space complexity.
Okay. So A star is complete and optimal because, well, the drawback of heuristic function is that it is not optimal. So it may like oscillate here and there, but A star search is complete and optimal in yes. And for time and space complexity, because you need to expand all nodes like this, where is it? Yes, this case where you also expand every single node, and your space complexity, well, is actually like the depth of search. Oh, sorry, breadth of search, as you're not focusing on like reaching all the way to the end, but you are going like level by level. You do consider this option. You also consider this option when you're at this point. If your depth first search which has linear space complexity, then you just focus on going on and on and on. So both your time and space complexity are also exponential. And well, this can be expensive if your state space is very large. Does this answer your question?
Oh, yes, thank you.
Okay. Anything else? Okay, then we'll move on to the next part, which will be called by Philip. Philip,
Okay, thank you, Jinan, for talking about search. So I'll be going on talking about constraint satisfaction and game playing. So why do we need to talk about constraint satisfaction is because going back to my example, the robot going to the finish line, in the event that we place an obstacle in the middle of the road, then the straight line won't really be the so-called shortest path anymore, because we have to move around it. If not, we end up hitting the obstacle. So that's why it's important. So the problem, so discover some state that satisfy the constraint set. So we add on one more thing. Just now we have the action state, the state space. So now we have another constraint set. So, and what is a definition of state? A combination of some or all variables arrangement with values in the domains. So what do I mean? So this is quite a wordy explanation. So I'll give you an example of what it means. So imagine this is a 4x4. It's called 4 queens. So we need to fill each column with one circle. Okay. So in the case where you're talking, I mean, supposedly I didn't fill this. I only fill one column because I'm still exploring my tree. Is still at the shallow part. That means this is initial state, none fill. Then I will go and expand to 4 because each I can fill my circle here. 1. This is the first location. This is the second location. 3rd, 4th. So then this will branch out further. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So in this one, only one column is filled. This one, 2 columns are filled. The next one, 3 columns are filled, and the bottom 4 columns are filled. So this is what it means by some variables arrangement. So not necessarily must be all the column filled, but it needs to have some state. Okay. So and the domains just mean where is the place I want to fill. So in this case, it is the columns that I want to fill. Okay. So I hope that's clear. So example in real life will be, let's say I want to solve a timetable scheduling issue. So this is really relevant also. Okay, so the variables will be timetable slot because I need to fit these timetable slots in my domains, which is the time allocated in the working days. I only have probably maybe 12 hours of working day. So I need to slot these timetables effectively and make sure they do not clash with each other. So that's a constraint satisfaction problem also. So any assignment that does not violate any constraint is called a consistent, it's called a consistent or legal assignment. So in this case, I will show you what this means later. So a solution to a CSP, a constraint satisfaction problem, is every variable is given a value. So in this case, all 4 states, all 4 columns are filled, and the assignment satisfies all the constraints. Okay, so I will show you the example now. So we are going to imagine a scenario 4 queens. So the criteria for this one is there can be no 2 queens on the same row, column, or diagonal. So if we look at this one, the first one, there are 2 queens on this row. So therefore, this is considered an invalid assignment. This one also, there are 2 on the same row. So this is considered invalid. But this one, 1, 2, 3, 4, is considered a legal assignment. So that's why this is considered, and all 4 columns are filled. So this will be considered a solution that we are trying to arrive at. So this actually is the final solution that we are looking at. So now we're going to discuss how actually we end up in this final solution. So maybe one method we can do is searching column by column. So as I said just now, the branching, the trees. So we can do this. The first one, then we branch out to 1, 2, 3, 4. And each one will branch out even more, 1, 2, 3, 4, each node. So you go dot, 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 until in the end, you have some amount of states. So you'll find out that the number of states that you will have is actually 4 to the power of 4 outcomes by listing all the possibilities and checking all. But as you can see, this space complexity and time complexity is big O notation of n to the power n. So for our case, 4 to the power 4 is only 64. It's still manageable. But let's say we have a grid of 10 by 10. That's 10 to the power of 10. So 1 with 10 zeros already. So it increased so much because the n to the power of n is a very big exponential function. So this method is not really good. So maybe we try a different method. So instead, we try expanding first. So we call this backtracking search. We expand it first. And we see that maybe if this over here, it does not satisfy what we want already. So it's violated already. Because over here, when it's not satisfied, it violated already. The further nodes that you expand below it will also all be violated. So why do you bother expanding this node? Don't bother expanding. So in the case where it's violated, just go backtrack and then expand again. So we put it in the second row now. Oh, it's violated again because it's same diagonal. So we go back here. So if you continue on all this, we will find the solution. Ta-da, over here at the end by expanding all this. So the key information for this one is you don't waste time searching when constraints has already been violated because the nodes below that will all be violated also. So there's no point expanding that node that's already violated. Okay. So, but you can see here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's still kind of a lot of things that we have to do. So can we improve this further? So how about we change this back? We change it to forward tracking search. Okay. So this is considered a more intelligent search because it factors in the implication of the current variable assignment for the other unassigned variables. So what does this mean? So if we put this dot here, the queen over here, we will realize that, we cannot actually fill in the row anymore. And we cannot fill in the diagonal anymore. So we fill in access over here. And so the next column that I fill in can only exist in these two only. So when I fill in over here, then I have to include more of the access again. So what happens is, I realize the third column is already all full with access already. So that means this is not a valid solution. So we have to go back. And then we fill in the bottom, then the left. So you can see that this reduces the number of states that we end up to about 3 only, which is much, much better than 64 and much better than this one. Okay, so this one, yeah. So other factors we can look at is, so the takeaway for this one is we have to keep track of the remaining legal values for unassigned variables. And we terminate search when the variable has no legal values anymore. So this means the third column has no more legal values. So we terminate the search and we backtrack it. Okay. So other more intelligent searches. So just now I already discussed one important method, and we also have 3 other heuristics to reduce our search size. So when I did these slides, I didn't know what's heuristic. So I went and used Wikipedia. So basically, it's something that helps you and it's practical, but it's not guaranteed to be optimal. But it helps you because remember just now, in the case of A* search, it was optimal and complete. But the problem was we have the space complexity we have and the time complexity will be a lot because you have to expand every single node to end up in an optimal solution. So for that simple graph, it might be okay. But for a more complex graph, it might take even days or years to run the optimal solution. So we settle for something that's just good enough and not necessarily the optimal solution. Okay, so one of the heuristic we can ask ourselves is which variable to fill first. So yeah, which variable to fill first. So in this case, we actually fill in the most constrained variable. So this will be another kind of another example I'm going to use. So this is Australia. So it can be represented Western Australia over here, Southern Australia, and NT, and Q, NSW, VT over here like this. So this is a nodal diagram of this diagram. So if I notice over here, SA is connected to 1, 2, 3, 4, 5. The edges. Okay, so the problem for this one is sorry, there's someone. Okay. We want to try color the map in 3 colors or try color the map with the least amount of colors. So if we fill South Australia first over here, means we don't have to compare with WA, NT, Q, NSW, and V anymore, because we already filled this first. So the rest have to just follow this SA, which means I eliminated the branching factor of SA already. Because if I were to expand SA later, it would branch out to 5 different outcomes. So why not I fill it first and make that the definite state? Then my branching factor for the overall thing will reduce. So as you can see just now, when we talk about time complexity and space complexity, we also talk about the branching factor D and the depth D. So if you reduce branching factor, you will indeed reduce the time complexity and the space complexity of this algorithm that we use. Okay. So the next one, we can also use a least constraining value heuristic. So in the case, so we choose the variable that rules out the fewest values or allows maximum flexibility in the remaining variables. So let's say we fill Western Australia first, blah, 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 and we end up here. Then we want to choose for Q, okay, should we put a red or blue? We definitely cannot put a green because green is already here. So, so I think I forgot to define the problem. The problem was you cannot have 2 colors beside each other. Okay, so we cannot fill in green here because if you fill in green, it violates that constraint a bit. So the only thing left is blue or red. Okay, so in the case of red, for Southern Australia, we will see that, oh, we can actually fit in blue some more. So we have one more value to fill in for South Australia. So in that case, we have this amount of flexibility left for South Australia if we fill in red over here in the first place. However, if we fill blue in the first place here, we realize that, oh, we already used up all 3 colors and there's actually left nothing for us to fill here. So there's 0 flexibility for South Australia. So of course, we want to make sure we color the whole map. So in this case, we pick up the maximum flexibility one. So we select this one. So we color it red instead of blue. Okay, and this can be carried on further to solve the whole map. Okay, okay. Then last heuristic we can talk about is we can assign initial value for each variable. And so in this case, later the video, we will use a greedy algorithm for the initial filling of values. And then what happens is we look at this queen, we call it. So just now it was 4 queens. Now this is 8 queens. So we look at this queen and we look at this state over here. If I put it here, okay, how many constraints will it violate? So if I put this queen at this spot here, it will violate this row 1. So 1 constraint violated, but you also violate this diagonal one. So 2 constraints violated. So I will fill this number as 2. And same thing, if I put this queen, let's say at this tree, position 3, I will get a violation with this queen. I'll get a violation with this queen. I'll get a violation with this queen. So I'll write a number 3 here. And if I fill in the value of rows, I'll get these numbers. So what this mean conflicts heuristic tells us to do is we shift this queen to a domain with the minimum number of violated constraints. So we can shift it here to this one or to this one. Then when we shift it here to this one already, right? Then this one will be violating this already, right? So then we apply the same logic and we shift it again. So we shift this one away. So I think I can show you a video. It's better to demonstrate this effect. So first of all, we fill it randomly. So the red lines is basically conflicts and what we are going to swap it with. So you can see they just keep swapping around. So I'll pause it here. So the video you can see is 41 seconds. So I think the disadvantage for this heuristic is it actually might not reach the end goal. So it's not a complete heuristic. So that's the downfall, because random guessing, you might actually be stuck in a particular node or branch that does not actually contain the solution. So you're just wasting your time exploring the solution. And or it might take a very long time to get out of that branch. Yeah. So in this case, this heuristic is also known as a local search algorithm, because you're only looking at stuff beside. So in the case of where you're talking about the nodes, right? So you're talking about, okay, you're talking about the nodes, right? Let's say I expand this node here. So let's say I'm at this state now. I'm doing a local search because I'm jumping from here to maybe a node here. I'm only staying within this so-called region. Imagine the tree is very large and it branches out very big, but I'm only exploring this part. So that's why it's called a local search. Okay, so yeah. Wait, okay. So is there any questions for this heuristic portion first before I move on to the next section? Anyone?
We can go back one slide.
Yeah, okay.
What's the 1 value for SA and 0 value for SA? I can't miss that, sorry.
Oh, SA is Southern Australia because this map doesn't have the names of the thing. So basically, you fill in, you're at this point, right? You are branching out. So you want to know whether you have to fill in red or blue. So the constraint for this side is you cannot fill 2 colors beside each other. Okay, and you only got 3 colors, green, red, and blue to fill beside each other. So if I fill in red over here, I will realize that for Southern Australia, this part, I can only fill blue left. So that's why I have only 1 value left for Southern Australia. But if I fill in blue over here, I realize that I have 3 colors used already. But then, see, if I put red here, it will violate with this red over here. If I put a green here, it will violate with green here. If I put a blue here, it will violate blue here. So there's actually 0 values allowed for this SA anymore. Yeah. So in the end, I choose this top one instead.
All right, thank you.
Yeah, okay. Are there any questions? Other questions? Okay, I think if there's none, right? Okay, I think I'll move on to the game playing. So, so far most of the AI problems that we try to solve, right? You will notice that we use games as a very good example to demonstrate the power of AI. And the reason why it's used as a benchmark in AI is because it's an ideal representation of real world problems. Like it can be abstracted. So it's a very simple thing where you can just run it in a loop for many times without, if you run a self-driving car in the real life, you might crash and you think it might cost money. But if you run it just simulation in a game, you can run it without any so-called very expensive cost in that sense. And also some games have uncertainty, which brings you to this contingency problem. So the reason why it brings you to this is because for certain games, you might have another player. So the uncertainty comes because you don't know what the other player will actually do. So and sometimes in an inaccessible environment, you don't really know what your effect will have, your actions, how you will affect the environment. So in that sense, it introduces some amount of uncertainty in the representation. And also it is complex, some of them. So example for chess, we have very simple rules for each of the chess pieces. But if you were to expand the chess, every state you will have a very huge branching factor, and it is not possible to expand all of it. I mean, it is possible, but it's not it's intractable, meaning that it's not possible in a reasonable amount of time. So, and furthermore, real world problems to note might not even have an end state. Yeah. So another unique thing about games is because in real life scenario, we probably have time limitations. So we probably don't want the program to continually search forever. So coming back to our search efficiency and why a good enough solution is used, and normally it's not optimal. So that's why games normally in fact, like Mario, they track the time as your score also. So if you finish the game in a faster time, you actually get a better score. So the score can be used to help to be a metric to see whether your AI agent is performing good. Okay, so I think, does anybody know this news that came out? So this one is AlphaGo. It's an AI actually that beat the world champion. And it came out in headlines in 2016. Yeah. So So this is an example of how games are used, and the reason is also Go is a very complex game. So for AI to perform and beat a champion is really it's kind of a big thing in this AI industry lah. So I have another quiz for you guys. What type of environment is chess? Sorry, press wrong one. Oh, you have a question here. Yeah, you PM this. Okay, I'll end it in 5 seconds. I think this one is quite a straightforward question. Okay. Do you guys need more time? Okay. So yeah, again, most of you got it correct. So the reason why is perfect information, I actually mentioned that in my slides earlier. It's because all the pieces are available for you to see. There's nothing to hide. Why is sequential? Because what you do this round will affect the game as a whole. So it's not episodic. Okay. And why is it static? Because you have some amount of time to while it is your turn, the other player cannot do cannot act. So when it's your turn, it's your turn. That's why in that processing time, the environment doesn't change. That's why it's static. Okay. So I think I'll stop sharing. Okay. Okay. So let's go back to our slides. Okay. So for games, we actually use a slightly different strategy. So we minimize one's own utility and minimize the opponent's utility. This is so long. What does this actually mean? So think when you're playing a game, when you want to win a game, you will obviously try to do the best thing. Okay. And similarly, or choose the best move in that game that will lead you to the highest end score. Similarly, your opponent will think the same thing. So that's why our assumption is we assume that the opponent does the same thing. But if the opponent is trying to maximize his utility or their utility, that means they're in a way minimizing your utility, right? Utility, yeah. So in that sense, in certain rounds, we need to maximize our own one. And in certain rounds, we need to minimize our own one because we assume that the opponent maximizes their own utility. So that's why you have this back and forth max and min. That's why this is called min-max search strategy. So in a perfect decision where no time limit is exposed, what we can do again is we can generate the complete game tree from initial to terminal states. So example over here, generate all. So we calculate the utility of terminal state and back propagate to the parent of terminal state, repeat. And then we repeat the process until the initial state is reached. So we calculate this utility of terminal state. So we realize that maybe 3 is a maybe not so good win for us. So we assign this a value of 3. This one maybe is a draw, so 5. 2 maybe is a loss. And 9 is maybe a win for us. So these are values that we can assign to the final state to maybe help us to determine numerically what the end goal means. So now we have to back propagate it. So in this, I will show you the exact procedure next. And then in the end, we select the move with the highest utility value. Okay. So note that this actually utility function, we've been talking a lot about this. It's just a numeric score to quantify the outcome of the game. So as I told you, this one might be a not so good. This one is a draw like that. Yeah, it's just a numeric score. So we will use these scores to find out which is our optimal solution. Okay, for in this case, we have 5, 3, 4, 7. So let's say our opponent is playing this round. So obviously they will try to minimize our utility. So in that case, we pick the minimum of this, so 3. And then we pick the minimum of this 4. And let's say this round is our round. We pick the maximum of this utility 4. So we pick this one. So if you find out that you go this path 4, 4, 7, it might be your highest. But in reality, will you be able to reach this 7? You might not be able to reach because your opponent, you might not be able to reach the highest score possible because your opponent is also trying to beat you. So instead of maybe getting a 4 or 3, maybe you get a 5. Maybe that's better than nothing. So in that case, look, if you minimize this, oh yeah, you select 3 now. And then for this case, you go maximum 5. So getting like the second best utility is still better than getting the other worst ones. Of course, if you expand the tree a lot, you will get many other worst ones. But if you remain, so this is what I mean by not getting maybe the highest score possible. Okay, so this one is perfect decision. We've been talking about how algorithms might not actually find the optimal solution, and there are no time limit exposed to this one. But in earlier, I told you that it's actually time limited. So we have to look at imperfect decisions also. So again, come to this terminology, intractable, meaning that it is not possible in a reasonable amount of time, because some games have a large branching factor like chess. So we have to modify the min-max algorithm. Instead of a utility function, okay, we use a utility function, right? We replace it with an evaluation function. It might be similar to Jin Han's one, but I'll explain more here. And instead of doing a whole tree search, we only do a partial tree search. So maybe we expand the node locally only. So like just now, I drew a lot of nodes, right? We might only focus on expanding this a depth of 2 or 3 before, and if we don't find our desired outcome, then as we move down the nodes, we expand the nodes further. So we expand maybe a small window compared to expanding the whole tree, which will take forever almost. Okay, so what is the evaluation function that we use? So there are actually numerous heuristics again we can use. It really depends on the problem you're working on. So example, if you're talking about tic-tac-toe, maybe you have one guy that's very, very expert at tic-tac-toe. So he's called a domain expert. So maybe that guy can explain that advice on the probability of each state winning. So imagine you have a state of circle, circle, X. Then that guy is so expert, he can tell you straight away, oh, this state has a 0.4 chance of circle winning, this state has a 0.6 chance of X winning. So that can be our evaluation function. Or in the case of actually our AlphaGo, they actually use a neural network to find the evaluation function of each state. Yeah. So this is where neural networks can also come into play in AI gameplay. Okay, and I think that's all for this section. And yeah, you have another quiz. Yay. Yeah, if anyone has questions for this section, in the meantime, you can just shout it out or you can type in the chat. I think if you guys can't see the poll, right? Are you guys using the web browser? Maybe the web browser doesn't support, but the app should be supporting it. Purple. Okay, I think that's enough, right? So share results. Okay, so which function is involved when the agent is deciding which choice to make when have no time limit imposed? Answer is just utility function over here. utility because we have perfect decision and no time limit as exposed. So I have one question asking me what is propagation function. Actually, propagation function and min-max function, I made it up. They don't exist. The legitimate answer is only A and C. For this question, is only is A. Okay. Okay, so I have one question asking me. Wait, let me stop the results. I have one question asking me what is evaluation function again. So evaluation function, you don't need to know the details about it, but basically it is a function to approximate the utility at that place, at that particular state. So it really depends on the numerous factors. It depends on the game. So like I said, you can be it can be domain expert that tells you each state approximation, or you can even use a really complex neural network to actually find out the functions. But the details of how to find the evaluation function, no, you don't need to know at this point. I think it's a bit too complex. Yeah, does that answer your question? Okay, if others have any questions, also you can ask it. Okay, I think there's no one. So we will move on to the most interesting part of today's session.
Okay, yeah. Okay, so well, we are at the last part of our workshop today, which is about agent decision making and reinforcement learning. So reinforcement learning itself is a huge domain. So we are just giving a brief overview that is what is required from this course. So first we'll start with the utility theory. So the expected utility is, well, what you expect from the probability that the expected value of something is the summation of the probability of that variable taking on a particular value times the value itself. So in this case, for expected utility, it is the utility that results from your next state after you take this action A multiplied by this the probability of reaching this next state result sub I of A, given that in this environment you carry out this action A. So okay, so I'll explain with this diagram. So your current state is S, and when you have many actions to choose from. So this first layer is your actions to choose from, and yeah, we'll cover this later. And then after you have chosen your action, and you reach this chance node. So after you reach your action, you can also have many outcomes. So for example, if okay, so I decide what do I want for lunch. So I go North Spine. So my action is to go to the North Spine canteen, but I still have, well, a lot of how do I say, a lot of results or choices. So we can, so for example, this one is mala, this one is ban mian, this one is Thai fan or whatever, or Western food. So, well, yeah. So from your principle of maximum expected utility, your agent should choose the action A under the environment E that gives the highest expected utility. And environment E is the environment itself is how defining how the agent interacts with it. And yes, we have an agent environment interface which describes how the agent interacts with the environment. So when your agent carries out this action A sub T, your environment will then give it feedback in the form of a report and the next state. So for the taking of self-driving car as an example, so your agent in this case is self-driving car, and environment is the traffic itself, and action is, well, go straight, go left, or go right. Okay. So here in this course, we discussed the Markov decision process, or MDP. So this is a type of sequential decision making. And one very important property of this process is the Markov property, which is the guy whom this process is named after. So it states that the transition properties depend only on your current state. And it doesn't matter how you reach that state, which path do you take to reach it, everything doesn't matter except what state are you previously in. Okay, so an MDP is actually a tuple of 4 variables: state space, action space, transition model, and your reward function. And this policy, pi of S, is actually the solution for this MDP. So state space is the set of all possible conditions or state of the agent. So it could be like at best, going straight, going left, or, well, no, sorry. So state space, okay, for a self-driving car, it could be doing well, almost an accident, or it crash. Okay, so action space is a set of actions that the agent can take at any state S. So if your state S is crash, then, well, you can't do anything, right? But if you're going well, then your action space may be, well, I can turn left, can turn right, or I can go straight. And your transition model is actually a probability distribution that your agent will reach the next state, which is S prime, from your current state S by taking action A. So this is actually a conditional probability. And then your reward function is defined as the reward for reaching state S. And the goal of your agent is to maximize the sum of these rewards. And this is defined as the utility, and we'll talk more specifically about this later. And your policy is the optimal action to be taken at state S, pretty self-explanatory. Okay, so the utility of state sequence here, we need to define something for our agent to maximize. So again, our goal is to have an optimal policy maximizing the expected utility of EU, I will just say EU, over all the state sequences. So this is the true utility of a state. So it's actually this true utility is the expected utility of all state sequences. So you have many state sequences, and then you average the utility, and that's your expected utility. So if you're just simply summing everything up, you have a problem if your state sequences are infinite, which means that you are going to have an infinite sum, which doesn't make sense. So here, to solve this problem, as well as to help our algorithms converge, we'll introduce a factor called the discount factor gamma. So this is a real number between 0 to 1. And so being 0 to 1 means that if your exponent, or this power, is higher, then it is closer to 0, then at some point onwards, well, you truncate this expression and you have a finite sum. So recent rewards, meaning the rewards from more recent states as not as 1, will count more than previous rewards. So for example, if your discount factor is, well, 0.5, so gamma is 0.5, gamma squared is 0.25, then gamma cube is 0.125, and then all the way until 0.0625, blah, blah, blah. Then you go closer to 0, and the rest you can just ignore them at some point. So the optimal policy, this one, to maximize the expected value of this one, is defined as the argmax of which action at every state S, which maximizes this thing here, which is the expected utility for a state S. Okay. So now we have a Bellman optimality equation to solve this. And then, okay, to derive this, the Bellman optimality equation is this. So to derive this from your, your sequence utility. So, okay, so you factor out this factor gamma, and then, okay, please pardon my writing. So factor out this gamma, you have R of S1 plus gamma of S2. Okay, so this part is actually similar to this part here, except that in this case, sorry, very ugly. So in this case, it is actually the state sequence utility starting from state S1 instead of state S0. So you can write this as this thing here, as we mentioned earlier. That, oh, sorry. Okay, I want to go back there. Oh, yeah. Oh. Okay, so this maximum value of this, which is, oh, sorry, let me clear this. So the utility, which is sorry. Okay, so the utility, which is this thing that you're trying to maximize the expected value of, is the u of s equals to the max of the expected utility. So here it is just this form here, which is well similar to this. So you have two ways to solve for this u of s, which is value iteration or policy iteration. So both are also fixed point iterations, but the difference is value iteration you solve directly for us, but policy iteration you solve for this pi. So for value iteration, you carry out fixed point iteration with this equation, but policy iteration you carry on with this. So after you have an initial policy pi naught, you substitute it into this equation here, and then you evaluate this, which is this formula over here, and then you carry out fixed point iteration over and over again. So we have an example of value iteration. Wow. Okay, so we define a problem here. So the two cells have reward as shown, which is this two, +1 and -1. So all the other cells have reward negative 0.04. So assume discount factor gamma of 0.9, and this cell we treat it as an obstacle. So we use value iteration to find the optimal utility, which is this, and similar to what we covered earlier. And then our action space in this case is you can go up, down, left, or right. And your transition model in this case is if your agent decides to proceed in a given direction. So if you decide to go up, then can I see it? Okay, so if your agent decides to go up, it will have a 0.8 probability of actually going up, and the rest it might go left or it might go right. So it happens at the random manner. So blah blah blah. If it hits an obstacle, it will remain in its original position. So for example, if it's here, but you want to go up, but there's an obstacle here, so it will remain at this spot. Okay. So earlier we said that the first step is to initial all the u0 in this case to 0. Then we try to do 2 iterations. So the first iteration of this cell 2, which is this, is where we plug in this equation. So the reward of all cells except these two are negative 0.04. So negative 0.04 plus discount factor gamma times. So now we need to decide on this maximum. So we think about, at this case, if we try to go up, okay, if you try to go up, but there's an obstacle here, which is the wall, so it will bang and remain at the same spot. So it's 0.8 times the utility at this point, which is 0, Yes, because it was all initialized to 0. U0 of S is 0 for all S in the state space S, big S. And then so this is actually all 0. Well, not much difference here. Blah, blah, blah. And your this thing here, which is negative 0.04 plus 0.9 times this, and this whole thing all goes to 0. So your initial, no, not initial, your U1 is actually this. And your S here is this cell 22. So if you repeat this repetitively, you find that yes, you find that all cells except this one has the U1 of negative 0.04. But for this cell, the reward RS is actually 1. So in this case, value is 1 for U1 of cell at row 2, column 3. And similar for this as well. So U1 of cell at row 1, column 3 is -1 plus 0.9 times something, which is 0, this part. So this is -1. So that's what I covered earlier. So this part is calculation. And we move on to the second iteration. So U2 of the cell 2, which is again this one, is equals to the reward for this cell, which is negative 0.04 again. Sorry. So it's negative 0.04 plus 0.9 times the maximum of this thing. So now U1 is not all 0 as before, so we need to consider it separately. So okay, so at this point, okay. So at this point, if you go up, then it will bang and remain at the same place. So 0.8 times this U1 of 22 plus okay, if it go up, then it might have a 0.1 probability of going left or right. So again, 0.1 times the utility of what if it goes left, which is cell 21, plus 0.1 times U1 of 23. So from our calculation here, we will know that for this thing, so everything here is negative 0.04, and this one is +1, this one is -1. Okay, so this one. Good. so this one is negative 0.04, and this one is negative 0.04, and this one is 1. So is there? I think so. Okay. Is it? Okay, so if it goes up, then this portion here is 0.064. But what if it goes right? Meaning that you have a 0.8 probability of going here, and 0.1 of going up and back and remain at the same spot, and 0.1 of going down. So the utility of this is okay, I erase it. So here we have, if you go up, then it's 0.064. Okay, what if it goes right? Then it's 0.8 times U1 of 23 plus 0.1 of going up, which is actually remaining at the same spot, 22 plus 0.1 goes down, so 1, 2. So this is 1. Yeah, okay. and 0.1 times negative 0.04 plus again 0.1 times negative 0.04. Because both of these are actually negative 0.04. And then, okay, what is this? 0.072. Is it? Okay. Oh, sorry.
0.0792792.
Huh? What?
792. No zero. No, yeah, 0.8 minus 0.0008.
Wait, hold it. Sorry, guys. My brain is not working. Okay. Okay. So if we go right, there is 0.792. Okay, what if we go left? Okay, if we go left, then we'll have 0.8 going left. And then we'll take this cell and remain at the same spot. So it's U1 of 12 plus 0.1 of going down or up. So U of if you go up, and this one is if you go down. And all of these are actually negative 0.04. So this is negative 0.04. Oh, sorry. So if you go left, then it's negative 0.04. So okay, what if you go down? So if you go down, you have 0.8 probability of reaching this cell, and 0.1 of reaching this cell again, and 0.1 of reaching this. So, so 0.8 of plus 0.1 of going left and remaining in the same cell, 0.1 of going right. So both of these are negative 0.04, and this one is negative 1. So this is negative 0.132. So if you go down, this will be negative 0.132. So we have this portion here, and we are going to maximize it. So we'll take this 0.792, then we times 0.9, which is 0.7118, I think, or 128, sorry, 0.7128. Yes, and then we'll add this RS, which is negative 0.04, and then it's 0.6728. Okay. Yes. Yay. Do that make sense? I hope I do. Okay. Oh. Can you guys see it clearly? Yeah, I think we'll send it after the workshop. Okay. So for now, we'll move on. Okay, so what if we don't have this very important thing here, which is this probability distribution, as we need it to go to decide whether we go up or down or whatever. So in this case, we will introduce the temporal difference prediction. And this word temporal itself is referring to the concept of time. So, okay, so this V is actually the same thing, but different notation. So it is still the value function. state value function or utility function. So we, at every step, we update it plus another factor, but in this case, we'll call it the learning rate. But both are also, it is also the same real number 0 to 1 as the discount factor earlier. And well, the discount factor is appearing again, and blah, blah, blah. So we'll try to explain it one by one. So with these two terms is actually this one. So remember that this thing is actually, well, again, this, okay, okay, let me try to write something. So this thing is actually the U of S prime. Okay, so, okay, so if in your temporal difference, well, what? So in your temporal difference, this thing is actually an unbiased estimate of this thing itself. Do you see the similarities? U, well, in this case, it is V of ST equals to R of S. This notation T.1 is because we assume that your agent will only receive the reward at the next state. Sorry, at the next time step, but it's still from the same state. Plus gamma, well, gamma is here again. And this thing, and I said, is the U of S prime, which is the utility of the next state. So this thing is actually, we call it an unbiased estimate of this V of ST, and we call it the TD target. TD target. TD target. Okay. Okay, so as I mentioned earlier, it does not require a model of the environment, which is the transition model. In this case, the P, this thing. So it is fully incremental in the sense that it can learn before or without knowing the final outcome. So it will refine its prediction over subsequent time steps, and it will eventually converge to your optimal state value function. So this may look similar to if you know the gradient descent equation. So for some parameter theta, we have at each state of the gradient descent, we update it with another value. Well, this is the partial derivative of the loss function with respect to this variable times the learning rate, which is again alpha, but theta minus this to get closer and closer to this prediction. So if your loss function is this, then if your initial theta is here, so you're minusing this term here to get closer and closer and closer and closer to this point where this thing is equals to 0. So there is no more change. So in this case, you can also visualize it similarly. This thing, you update it all the way until this TD target is closer and closer as possible to this the actual value. So in this case, it is 0 and, well, no more update anymore. So we can say that your algorithm has converged. Okay. So pop quiz. I will now share the poll. Where's the poll? Okay. So does the value of alpha affect the convergence of this state value function? Well, you can relate to the gradient descent algorithm that we have covered earlier. Interesting. I know. What? I know. Interesting. Do you have questions in the chat? Okay, 10 more seconds and I'll share the answer. Okay. So the answer is B, and I'll explain why. So A, alpha depends only on the number of possible states. No, it doesn't matter at all. Well, alpha is in the sense something that you choose when you're trying to run your iterations, and it does not depend on your number of states. So your number of states could be 1, could be 5, but it does not affect this alpha. And C, rate of convergence depends solely on gamma. No, gamma doesn't affect that much. And D, the value of alpha must be larger than 1. No, in deep learning, when you are doing gradient descent, you seldom set alpha to be larger than 1. In fact, you never set alpha to be greater than 1. It's typically in the range of 0.001. So for B, okay, I'll not explain with this funny graph here again. Okay, so say if your alpha is 0.1, so your starting value is here. Then your 0.1, okay, assume first alpha 1 is 0.1 and alpha 2 is 1 times 10 to the power 1 times 10 to the power of negative 10. So for alpha 1, your update is on every step you actually take a greater step ahead. So okay, let's just take some absurd number 10. Please don't do this in practice. So in every update, you have, okay, so for example, we just consider the partial derivative to be, sorry, where are we? To be a constant value of 1. So in this case, you go 10, and then here you go, I don't know where again. So you just go around crazily. Ding, 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 you go around crazily. And then you may again overshoot. And then here you may somehow get there again, I'm not sure why. But if your value alpha is very small, then you will take a final step at each, well, no, sorry. Okay, so you take a smaller step at each point. Wait, why eraser? Oh, okay. Wait, sorry. Oh, okay. Okay, okay. So for if your alpha 2 is very small, then you have a small update at each time step. So slow and steady, and then you eventually reach the lowest point, which is your goal. Well, this is an deep learning analogy, but it may not be completely correct in this sense, but it helps you to visualize the importance of this value alpha. Okay, so I hope this explains this. Please. Hey, wait, I didn't share the results. Sorry, guys. Oh, you said already. Okay, so answer is B. Okay. Okay. Okay, so that's the end for all we have. Well, any questions? Chat, anything? No. Any questions? What do you mean? Swap. Swap. For the photo, right? Wait, which is okay. Is there questions? Which chat? Oh my god, yes. So it's here. Oh wow. Okay, so there are some questions in the chat. Okay, so How many questions in total? That's the end, actually. Okay, and evaluation function. What? Yeah. Oh, we have 5, right? Oh, the real quiz. Jihan, do you mean the real quiz? Oh, okay. How many?
Actually, not sure because
Please check and you learn.
and the question might turn out very weird, like how midterm was. So don't be so stunned if it come up weird stuff.
Just pray for the best.
Yeah, just do your best, but try to understand all the concepts as well as you can.
Evaluation function, have you explained? What is that? Okay, how do you determine it goes left or right for your valid iteration example? Where does your theta come from? Okay. So theta is just some variable that I made up for our example. So as for y, it goes left for you. As for y, it goes left or right. Okay, so again, this is your loss function. And assuming you only have one parameter theta, this may be your okay, so for example, if you're doing linear regression, then your theta is the sum of squares, and your L is the, well, you can be mean square error or whatever. So if your graph is like this, let me draw something weird. So okay, if you start at this point, so again your iteration scheme is theta equals theta minus alpha times the partial derivative of this thing with respect to your variable. So in this case, your derivative is positive. So alpha is also positive, so it will minus. But if this is in the case where if your alpha is small enough, but if your alpha is too big, meaning that if you go too far to the left, so in this case it might go, I don't know, here, okay, it may go here. So if it goes here, then your derivative in this case is negative, slope going down. So negative times negative, well, you are going to the right again. So you are oscillating wildly without actually proceeding to the solution itself. But if your alpha is small enough, you then, well, kind of like stable oscillations. So you just go at a small step at every time, and then it will reach this solution. But if your alpha is too big, then, well, it will go like unexpectedly going left and right without actually reaching the solution at all. So yes, is it clear? May I ask if you need to memorize any of the formula? Okay, I guess you should try to remember this one. And also the policy iteration.
I think in terms of literal what term and what term, no, because it's going to be MCQ, right? But you need to understand what you are doing, why you maximize it. So then if you understand why you maximize the utility function, the value iteration function, then you will know that there's a max, the arc max inside that formula. And then you need to understand why you add back the RSS.
Let me just.
Yeah.
So maybe the important thing is the value iteration and the policy iteration. Any other questions? I see the chat. Okay, thank you. Okay. Okay, so feedback time, I believe. Yes. So it'll be great if you guys can scan this QR. Can copy the link
Oh yeah,
to
sure.
the chat.
Oh, you have. I don't have the slide. If you guys have any questions, you guys can stay back later. We will address them. Yeah. But now we are feedback. And wait, guys, don't go first. We got
We have
photos.
photo session.
If you guys don't mind, you can take some photo for publicity.
Yes. Okay, so stop sharing. No more, right? Yes, photo taking, guys. Yeah, I'll send the link for the feedback to the chat. And please don't feel shy on your webcam.
How are you?
Screenshot.
Yeah, if you guys don't mind, we can help you. You guys can on your webcam. Yeah.
people. Everyone gone. Okay. Okay.
Yeah, I see one person here.
Hmm?
Wait. Why they don't move the picture up?
Very loud.
Okay, wait, I need to arrange you guys because okay, I think that's it. Yeah. Wait, go and take picture. 3, 2, 1, smile. Okay. Wait, let me check whether I took properly. Okay, I took it properly. Okay, thank you guys. If you guys have any questions, you guys can stay back. Otherwise, you guys can leave already. We will send the slides and the recording link to you guys later. Check out your email. Yeah. Thank you.
Thank you. Bye,
guys. All the best for all remaining exams.
Bye. Good luck. Good night. Okay, so there's a question in the chat asking, what are you calculating in the end? So the U is actually the utility function, which we define as the expected value of the discounted sum of the rewards of each state. So it's called a utility function or the state value function. And that's what your agent is trying to maximize. And we are going to find the value itself by either the value iteration or the policy iteration. Okay. Oh.
So if you follow in other words, if you follow the maximize path every time, you will end up with the best path in a specific scenario. Because in the end, that's the end goal we're trying to find.
Is that clear enough?
You guys are here. You guys have any questions?
It's the best path determined by type. So this is like a fixed point iteration where your value. No, I think. Wait, time more. So well, it eventually converge if you carry out infinitely many times. But if you see your value is fluctuating around the same constant value, then it's converged already. So, well, it's actually not the best path. It's not the best path. It's just trying to find the values of each individual cells. And you're trying to see whether the value is constant. If the value is constant, then you can say it converge, and yeah, that's it.
Another representation of your question, best path, right, is depends on the problem we solve. So in our case, right, is a robot deciding whether it wants to go straight, left, or right. So in that case, your so-called you want to minimize the distance traveled or the time taken to travel, because maybe, I mean, distance and time is about the same in this context, because if you're talking, maybe if you move in one direction, it takes same amount of time. So if you minimize the distance all the time, you get the same thing. But if in another scenario, which I cannot think of now. Okay, come on. Yeah. How about the others? You guys have any questions? If guys don't have questions, actually you can leave it. Because there's 10 more of you guys. I thought you got questions. Yeah. Okay. Yeah, he gets it. Yay.
Okay.
Any more? Any more? Any more?
Yu Wai Yong, do you have any questions?
Yeah.
I have a question. Why you remove me?